The purpose of the term paper is to give you an opportunity to look into something that interests you in greater depth than you'd have time for in the course, and possibly to find a thesis topic. Before we leave the subject of sediment beds and erosion, I point out that the cohesive sediment beds generally are smooth, hydraulically smooth. That means that the height of the roughness elements are less than the thickness of the viscous layer. There's a picture on page 63 you might look at when you have an opportunity of a sediment bed, and you can see it's almost featureless. It's there's a little roughness, but typically their roughnesses are very small. Now the exception to that is when a bed is eroded down to, say, shale or bedrock, where it may break off in clumps and be rough. But typically a bed that's formed from depositing sediment is smooth, hydraulically smooth. So you can use the hydraulically smooth formulas. On the next page is a picture of an electron, or of an optical microscope, a micrograph of some sediment from that bed. And you can see that it's made of aggregates that are roughly spherical, rough spheres. Some of them are a little bit elongated like a bunch of grapes, but typically they're rough spheres. Then on the following, on pages 66 and 67 are some contour plots of a sediment bed in the flume. That's a very distorted, those are very distorted plots. The flume is only 3 feet wide, but 100 feet long, so you can see that the width is spread out. The contours reflect the concentration of gold 198, a radioactive tracer that was put on the sediment to determine the deposition. And you can see that there's some gradient at the inlet end and some at the outlet end, but in between it's pretty smooth. At the inlet end, the pipes came into the flume vertically so that there was some swirling, and at the outlet end it converges to the pump so that there's also some swirling there. I passed out a bundle of paper to you, and I'll refer to this today at various times. And the first page is a bunch of logarithmic formulas, or the logarithmic formula with a bunch of different coefficients in it that reflect the different configurations. These are average velocities in the cross-section shown for circulars. The first one is for rough walls and smooth walls, or just an open channel, a very wide channel. Next one is for pipes, and the next one, I'm sorry, the first one is for, yes, a wide channel, and it gives you the actual velocity at elevation y. The second one gives you average velocity for pipe, smooth and rough walls. The third for a wide channel, average velocity for smooth and rough walls. The fourth, trapezoidal section. The usefulness of these is that, of this sheet, is that it gives you the coefficient, or the empirical number there that makes it work for that particular configuration. Today I'd like to talk about, begin describing estuarial hydraulics. I guess we started already talking about that. So far we've talked about sediment processes, sediment transport processes, aggregation, deposition, the nature of the bed, and erosion. These are the basic processes. Now, in order to describe the transport of sediment in a natural system, an estuary, we need to describe the motions of the water that carry the sediment, that do all of this. They're not simple as that in a flume. That is not simple unidirectional, except up in the river part of the estuary. They're usually typically oscillatory motions that where the water moves with the ebb and flood of the tide. Perhaps the best way to begin is to talk about the river input. I'll define an estuary as the transition between unidirectional freshwater flow and the tidal saline ocean. Okay, we have the ocean on one end of an estuary that rises and falls and contains salt water, and freshwater flowing in to tributary streams. The freshwater typically has very low salt content, but is not necessarily steady except in the short term. But it may fluctuate considerably during a season. The body of water in the estuary is affected by both of these boundary conditions profoundly. That is, each one has a large effect on the water in the entire estuary. In addition to that, we have winds that affect large bodies of water. Many bays are wide and shallow, so that the wind may have a dominant effect on the water. Describing these hydraulics is a little bit complex. We can describe it qualitatively, but to do it quantitatively requires elaborate mathematical models. So let me begin by talking about river inflows. The river inflows reflect the seasonal patterns of precipitation of the region. Now, a good way to begin is to just look at the rainfall characteristics of the region. On the East Coast, they may have as much rainfall in the summer as they do in the winter. On the West Coast here, virtually all of our rainfall occurs between the end of October and, say, the beginning of March, with snowmelt following into March and maybe early in April and maybe early June. So the local rainfall runoff pattern may vary widely, and it's important to take that into account in considering sediment transport in any estuary. In California, we have, as I said, most of our rainfall occurs in the winter months. So if we drew a hydrograph of time versus discharge of a particular river, say the Sacramento River, we get something that had, say this is January, February, March, April, May, June. We get something that has perhaps a lot of jagged peaks in it, like this. And then later in the year it would trail out, and toward the beginning of the next year it would begin to rise again. So what we see in an estuary is temporarily changing freshwater inflows. And as I indicated, in the arid west here, most of the water flows in during the winter months. In fact, about 90% of the sediment that enters San Francisco Bay comes in December, January, and February. It's if you go out and look at the bay, you see that it gets brown that time, and then the brown tapers off later in the year as the material moves out. Not only does most of the sediment and water come in during the few months of the year, but each year is quite different from the preceding one. Well, maybe not that different. We've been having drought for 5 years. But the sediment supply to an estuary and the water supply may vary over quite a wide range. In Southern California, I worked on Upper Newport Bay studying the sediment inflow, and it turned out that most of the sediment in that basin came in during one storm that occurred with a 20-year interval. It may be that the supply of sediment is really episodic. It may only occur once in a great while. So if you're looking at data on inflows to an estuary, you may find that you have to look at a long period of time to get a representative water and sediment supply input. On the East Coast, it's quite different. The flows are more or less constant all year round. and the sediment supply is more or less constant all year round. On the beginning on the second page of the handout I gave you today are tabular values of Sacramento River input. I think this is year 1978, taken from the U.S. Geological Service water supply papers. And I brought this to you to show you what's available in the literature. You need to know what the inflows are for back to about 1922, in the case of the Sacramento River. You can get the inputs from these tables. They're measured at least once a day in major rivers and recorded in minor rivers. Those of you who went on the field trip last spring may recall a recorder on the bridge at Rumsey. Remember the recorder? It was permanently mounted on the bridge. That records the water surface elevation at that bridge site. And the Geological Survey goes out and surveys the cross-section. They'll determine the cross-section. Under a bridge, it's usually confined, so it makes it a nice area. And then they'll determine the currents in a series of sections like this for various water surface elevations. They'll measure it at, say, 4/10 of the distance above the bed. That's representative of the average for a logarithmic velocity profile. Or sometimes they'll pick 2 points and average them in each of a series of cross-sections. They'll assume that the velocity is the same in over that cross-section, add them all up and calculate the discharge. They'll do that for a variety of flows at different water surface elevations and come up with a rating curve, often log H, let's call it, elevation H, against log Q. And they'll get some kind of a curve. Actually, they'll get quite a scatter of points because during a rising limb, it's different than during a falling limb because of the slope. But in any case, they'll get some kind of a curve like this, or they'll fit it numerically and prepare a table so that they can take the graph from that stream and determine the Q for different elevations. And those are the Qs that are reported here. Now, these are sediment discharge, tons per day. I'll show you Qs in a minute. And you can see that they're daily for each month. The water year starts in October because the system is back to a dry state the 1st of October, and it's called the water year or the hydrologic year. Begins in October and ends in September 30th. So it includes the entire storm high flow runoff period. You can see that there are daily values of concentration, sediment discharge tons per day, and the mean discharge in cubic feet per second, water discharge in cubic feet per second, for each of a number of months. If you turn on through that to this next third page, you see it gives a summary of water and sediment discharge water year October 1978 to 1979, and it gives a summary by month in terms of CFS days. And it gives suspended sediment, and then it gives bed load discharge. And I'm not sure how that one is determined in this report. I'm not positive, but I think it's that fraction smaller than silt size, 62 microns. Then on the following page, it shows the for the Sacramento River, the instantaneous stream flow, the temperature, suspended sediment concentration, sediment discharge, and the turbidity. So you see there's a lot of information compiled by the Geological Survey on major streams. On minor streams, you won't find all these data. On the following page, it gives the remainder of it. And then on page 151, the next page, it gives the particle size distribution of the suspended load. So there's really quite a lot of information on the discharge of the suspended sediment. And then finally, it gives the next page. It gives some discharge in a summary table. Water for water resources.
Good questions.
Uh-huh.
Under turbidity, it gives the units as NTU. Under turbidity,
Uh-huh.
it says NTU. What's NTU?
That's normal turbidity units. What's N stand for? Turbidity unit. What is it? What is it?
It's light comes in and gets scattered off to the side.
Oh yeah, that's the turbidity.
And turbidity, the light goes straight through it.
Oh,
Yeah.
I think that's N stand for Nestler?
No, methylometric.
Nephelometric turbidity units. Thank you.
Dr. Krone, I have a question. You said a little while ago that typically the sedimentation data varies from year to year, except in the last few years. What do you attribute that to?
The difference in rainfall pattern. The sediment comes from erosion of the land and the stream banks. And erodibility of the land depends on the moisture content of the soil when the rain falls. So if you have a continuous rain, you'll have less sediment of the same total amount of rainfall, less sediment produced than if you have rain and then it dries and rain and then it dries. The fundamental reason for that is that aggregates of soil, dry soil, wet from the outside in, and the capillary forces in the pores compress the air on the inside and make it explode, come apart.
I thought maybe you were talking about a geologic phenomena or a geological historical phenomenon.
No, this is because of the variation in rainfall and the distribution of rainfall in time. Might have something to do with anthropogenic factors too. If the fields are all plowed when it rains, it may erode more than otherwise. We're in the process of doing a sediment balance for the San Francisco Bay system now, and we have records from 1922 to 1990 that we're trying to organize in a statistical way so that we can get a sediment input so that we can predict some statistical sediment input in the future. And the variation over that period is really quite remarkable. Quite a lot. Well, so far as the river's input is concerned, there are good data. Oh, I must say, this geological survey data is available in our library and widely available in libraries. It has one real problem, and that is that they're published way late, sometimes 5 years after they're taken. So if you need current data, it's important to go to the geological survey and ask someone to Xerox their pages. They do produce another publication called Water in California, I think it is. Something like that, Water in California. And if you ask them, you can get a copy of that. It's published annually, and it has some more recent data in it. But I find myself over at the Geological Survey Xeroxing their records because they just don't get them published very fast. When you look at stream inputs in different estuaries, what you'll find is that some streams produce a lot of sediment and other streams produce very little. So often there'll be one or two streams that you spend a lot of time on and the others that you spend very much less time on. The only other thing I can say is that going around the United States as an example, the west coast I mentioned has rainfall in a few months in the winter months. Down in the Gulf area, the Mississippi and the Chafalaya and Red River all have more rainfall in summer than in winter, but it's snow in the winter and snow doesn't melt until spring, and then they have rain in the summer. So most of the runoff is in the spring when the snow melts, or later in the summer. The East Coast has about the same amount of rain all year round. So, you know, it's quite different from place to place. And I'm sure as you go around the world, you'll find the same thing, that there are areas where they have more rain in monsoons in India, for example, and than they do another time. So it's important in dealing with an estuary to look into the local rainfall runoff conditions and to get sediment data on input. And remember, if you don't have sediment data for at least a decade, it doesn't mean much because it varies a lot from year to year. Well, so much for rivers. We got by that pretty quickly. Now I want to talk about tides. And I'm going to repeat some material we had last spring, but there are quite a few of you in here that didn't have that, so I think it's worth repeating. The tides are driven by the attraction of the sun and the moon, primarily. So that the periodicity and paths of the motions of the sun and moon really determine the tides. We can describe this as the sun here, and the earth some great distance away here. I'll make it small, with a moon that travels around it, and the angle of the moon's orbit relative to the ecliptic of the earth is tilted. I've forgotten now how much it's tilted, but it's tilted, and the moon's path, its path around the earth, its orbit around the earth, has a 28-day period, roughly, and the orbit precesses, so that this angle here rotates in this way, complicating the paths a little bit. Furthermore, the Earth's axis is inclined about 23.5 degrees from the plane of the ecliptic, from the plane of its orbit, so that as it goes, and it maintains that angle, so as it goes around the sun and comes out to the far side, its angle is still changed relative to the sun. And it happens that in the northern hemisphere, the Earth is closest to the sun. The orbit isn't quite circular. The Earth is closest to the sun during our winter and farthest from the sun during our summer. So the northern hemisphere has a milder climate change than does the southern hemisphere, which is closer to the sun during summer and farther from the sun during winter. The Antarctic is much colder than the Arctic. I think you're all aware of that. So that we have this combination of the moon orbit, moon going this way, but the orbit actually precessing, so that the angle changes, and the sun, the Earth, going around the sun with a slightly varying distance from the sun during the seasons. The gravitational attraction is inversely proportional to the distance from the body. You know, all know Newton's laws. Gravity, the force is equal to a constant times the mass of one times the mass of the second body divided by r squared, the distance between them. And while the moon's mass is very much smaller than that of the sun, it's much closer to the Earth than the sun. So the moon's attraction dominates the tidal system. But the sun's still close enough so that it affects it. Now if we look at the forces on the Earth is attracted to these heavenly bodies, and the water on the surface of the Earth is also attracted. So the water tends to bulge. Let's say the sun is out here. The water tends to bulge out on the outside, on the side nearest the body, and because of centripetal force of the water relative to that on the Earth, it also bulges out on the far side. So the tide is high on opposite sides of the Earth at the same time. Keep in mind that the Earth is rotating under this process, so that on any one day, the sun may be in a direction that doesn't change very much, but the Earth is rotating under this bulge in the water, so that the bulge appears to us to be traveling around the Earth there. Because the moon's closest, it attracts it mostly, and the moon's orbit around the Earth has a period slightly different from a day. So that makes the this bulge go around the Earth pretty fast. And what you would see in the ocean is that this bulge is a wave, actually, that goes across each of the oceans, depending on the motion of the Earth and the moon and the sun. Well, that would make prediction of the tide very simple if it weren't for the fact that the wave interacts with the boundaries of the system, the depth and shore configuration of the system, which greatly modifies that wave. Well, first of all, you can see that when a wave hits a boundary, it's reflected in some way, depending on the shape of the boundary and the angle of the boundary to the wave. It's reflected from that boundary. So that in a simple system, if we just had a rectangular system with the wave going across it like this in this direction with a velocity c, when it reached this boundary, the wave would start to go back. At least some part of it would start to go back in the opposite direction. And when the time the time to travel this length L, let's say, let's see, how shall I say this best? The velocity c equals L over t, right? And when the time to go across this way and go back again equals the tidal period, then you see that there's reinforcement each time the tide goes. And the result is that you wind up with a tide going back and forth across this, what we call a standing wave. So the tide will be alternately high and low on the ends, and it will be higher than it would be if it were just unexcited, because each return reinforces the next tide. Do you follow me?
Resonating. It's basically like resonating.
That's resonance. Yeah, that's right. That's exactly what it is. Those of you who have children probably saw the children bathing, and put them in the bathtub and have them move their hands back and forth at just the right frequency for the bathtub, and the water in the tub goes up and down, and it gets higher and higher until it splashes over the end. I'm sure you've all seen that. That's resonance. That's well, that resonance is quite a common phenomenon in the oceans. The Gulf of California, Baja California, for example, is resonant. So they have tides on the order of 30 feet range. And the Cook Inlet in Alaska is another one where there are 30-foot tide ranges. And Bay of Fundy and the Gironde and the Thames and the Severn all have resonant systems where the range of the tide is quite high, and it has a major effect because when the wave typically looks in a resonant system looks more like at the peak height at that one, and then like this at a half a time t later, so that this range here is quite large in a resonant system. The velocities in the middle, the water has to move back and forth in the middle to make up this volume, decrease this volume and move it over here, and then back again. So the velocities in the center of the resonant region are much higher than they would, the tidal velocities, much higher than they would be in a simple system where a tidal wave passes. So one important phenomenon is resonance in the system. Another one is friction. When the wave is long relative to the depth, water depth, when it's longer than twice the water depth, the motion of the water on the bottom is retarded by the friction of the bed, movement on the bed, so that in shallow systems friction can have a significant effect. A third effect is peaking. If you have let's say an estuary whose plan plan view might look something like this. When a tide moves into the estuary, it's can be regarded as a wave whose crest length is restricted, so the amplitude increases. You've heard of the ear trumpets? You know, that's how an ear trumpet works. It increases the amplitude of the wave, so that having a simple estuary of that sort can also change the elevation of the tide, and if there's friction, it may retard its progress, may slow it. Well, all of these resonances and effects of the boundary on the motions that are excited by the Earth and by the Sun and the Moon make the tides quite complicated in any one place. And in order to make a tide prediction, it's necessary to fit data measured at various places, and I'll describe that in just a minute. Before I do, there's also in the library is the tide tables of North and South America and other areas. In the United States, it's the National Ocean Survey that prepares these, and they're widely available. You can also walk into any sports shop and get a local tide table printed for fishermen. They all come from the National Ocean Survey data and computations. These data are developed by putting tide stations at a number of points. In San Francisco Bay, they had something like 30 points, and up and down the coast in the area, and letting the recording stations and recording the tides over a period of time. Now, there's one at Fort Point that's been there since 1849, the longest continuous record in the United States, in fact. And they'll put secondary stations out so that they can correlate the readings of those secondary stations with the long-term station, and by doing that, synthesize a longer-term record for each of these local areas. And they take those records and fit them to a cosine series, which is they'll put the elevation, I'll call it H. H for the elevation is equal to some mean elevation, mean tide level, or, plus a cosine series over n. I'll explain n again in a minute, to some hi, I'll call it amplitude, times the cosine of 2 pi t over sometimes plus 1 or 2 coefficients. I'll call them a plus k. And they'll sum up a number of terms and find empirically values of hi, amplitudes of each of these cosine terms, so that they fit the observed data. Now, one question you might have, this t, the period, needs to be known in order to find this. They can adjust this one, and this is a second one. This is the cosine, gives you the amplitude, and this is the phase shift, okay? The second page after that title page that I showed you shows some tides at Anchorage, Dutch Harbor, Ketchikan, Seattle, and San Francisco. And you can see that the tide amplitude of the tides are very much larger than up in Anchorage at the head of Cook Inlet. Actually, it's on Nick Arm, which is off of Cook Inlet, than they are at, say, San Francisco, the top one up there. Also, you notice on this that the tides aren't a simple sine wave. They're what we call diurnal tides, two tides in a day, and that they change in character from one large amplitude variation, then a small one, and then a large one and a small one. And then as you go over to the right, they become, they change one from the other. And that's because of the change in the phase between the sun and the moon. Typically around the Earth, the tides are like that. They're diurnal tides because the sun and the moon have different effects. But there are places where the resonance and one of them dominate the system, and they have almost sinusoidal tides. In England, for example, you find almost sinusoidal tides. But typically, this diurnal kind of a tide occurs, and the amplitude varies depending on the local conditions. You can see there's quite a difference in amplitude just down the west coast of the United States. And on the next one, you can read at your leisure. Then the following page, it gives differences in amplitude in different parts of the San Francisco estuary. I just brought this one because I happen to have it handy. Different places in the estuary, and way over on the right you'll see mean tide level, and then you'll see ranges, mean range and diurnal range. I better define these. The tide might look like, in one day, for example, something like this, where this is H0, the mean tide. And this is time, and this is about 25 hours, roughly. The mean range is the mean of all the highs and lows, mean difference between all the highs and lows. The diurnal range is the difference between the highest and the lowest value. You can see that in San Francisco Bay, as you go upstream, the mean range gets smaller. And that's because of friction. I'm going to talk about San Francisco Bay in detail later. But it's because of the delay and friction of the boundaries of the system resisting the tidal flow of water. Then on the following page, and for a couple pages beyond that, it gives the hourly highs and lows of the tide. So it just gives the highs and lows. It doesn't give you the tide, the elevation of the tide in between these. And it doesn't give you any currents. It's just the tide elevation. And it gives it, as I say, hour by hour throughout the year. On page 171, well, we've already looked at that. I got that copied twice. I didn't realize that. It gives the outer coast and values up and down the coast. Then the following one, the Part 3 prototype data analysis, I took out of a typical report showing the way that it describes the way that you use this cosine series to describe the tides. And it gives on page 26, the harmonic constituents. And they've been given symbols over the years. And these are based on the periods of each of those motions I told you about and interactions between them. The periods in hours are the principal lunar diurnal, that is the principal attraction for the sun, is 25.82 hours. And then down next to the bottom it shows principal solar, and it's 12 hours. That's what you'd expect. Then there are all these coefficients, and typically they'll use maybe two-thirds of those numbers, or sometimes all of those numbers in a series, which means that you have quite a few terms that you have to fit coefficients for if you want to predict the tide, and that's done by the National Ocean Survey. Well, you can read that at your leisure. On the page that looks all dark, it looks pretty dark here. It shows a compressed year-long tide for San Francisco Bay at the Golden Gate. And you can see how the amplitude changes twice during a month, roughly twice during a lunar period, 28 days. So from a maximum to, which we call a spring, the spring tide, tide that looks like the maximum diurnal range is called a spring tide. This is time and age. And then it goes through a minimum where both highs and both tides during the day are about the same. And this is called a neap tide. And important that it goes through this spring tide to neap tide to spring tide in 14 days, that half of that 28-day period. So that if you want to simulate the conditions in an estuary over the tidal condition, you need to have at least 14 days of data, 14 days of tidal data. Then on the following page, I'll show you the results of a tide prediction, predicted tidal data for, this is the Golden Gate tide, and the difference between the predicted and the actual tide. And you can see it's not bad. There was one right at the neap period of neap tide who was off most of all. Now, the things that affect the tide besides the sun and the moon, which is what this coefficient determines, are winds and high freshwater flows. So the deviations like from the predicted tide can occur if there's an exceptionally high freshwater outflow, particularly in a bay like the San Francisco Bay that has a restriction at the Golden Gate. The high river inflows can raise the tide, or winds or low barometric pressure usually occur together. When a hurricane or typhoon comes on shore, the water level rises because of the low atmospheric pressure at the center of the hurricane. And that's part of the reason that hurricanes are so devastating, because the level rises, and then on top of that you have high waves generated by the wind. So the predicted tide can be considerably in error during storm periods.
Looking at this data, it looks like usually less than the real time, or almost the entire period is considerably less.
Yeah, in this case.
Is that typical, or is that just accidental?
Well, it's not far off from the Gulf. The Gulf has a very tide range in the Gulf is only about a foot or a little more. And the natural tide range and the wind range is about a couple of feet typically during a year, and when a storm comes it may be 5 or 6 feet. So, I think that's typical of the Gulf anyway. I don't know about the East Coast. Well, maybe so in the East also. So, but the difference is generally due to river flow and to low pressure and wind setup. Now on the next page, there's a nice illustration of what each of these cosine terms does. You can see that the moon, the principal moon one, has by far the greatest contribution to the series, and that each of the subsequent ones has less and less contribution until you get down to the M4, which has a very small contribution to all of these. Well, getting back to what I was saying, the National Ocean Survey sets out these tide recorders, and they go through this about once every 50 years in each location. Sets out the tide recorders, and then they correlate all of them to a master station or a couple of master stations so that they can synthesize an extended range in time, extended time of record. Then they subject each of them to this kind of a series and calculate the the HO and HI values. And if there's a phase lag, they'll calculate A also, using as necessary to accurately simulate the tidal changes. Then once they've got that series together, then they'll calculate the tide tables, predicted highs and lows, just the maximum and minimum. The maximum occur when this term is 1 or 0. So they can get maximum and minimum and produce these tide tables. The reason I went through all this is that I want you to recognize that projections of tides don't necessarily represent the actual tide you're going to get there. It may be different because of wind or high river flows, or it may change because of changes in the waterway. If you build a barrage out there, or a dam, or a breakwater or something, you can change it.
Yeah, question on page 57 where you're showing the various harmonics. What do the U2 and M4 harmonics have to do? I'm looking back at your listing.
Uh-huh.
And
Are they not on that table?
Nor is K2, I guess.
Oh, there are two more, and frankly I don't remember. They're the interactions between the sun and the things they take into account are the sun and the moon's orbit, then the interaction between the two, then for each one they take the opposite side of the Earth also. And the seasonal part of the year. In January, we're closest to the sun, remember? So the sun's attraction is greater in January than it is in June. And the amplitude of the spring range is higher in January than it is in June because of that. So frankly, it's been years since I read that, so I can't tell you exactly what the interactions are. Each one has a smaller and smaller amplitude, and adds a slight correction to the preceding one. So it's a Fourier series, essentially, just a cosine series. The importance of the tide to commerce, to ships being able to get in and out of a harbor, has motivated spending a lot of money on tide tables. Originally, they tried to compute them by hand, which, as you can imagine, is not very successful. Then they developed a machine, which was a series of pulleys, and the pulleys that added these cosine terms, and what they had was a drum. This is just historical interest. And the drum rotated with time. It had a clock mechanism on it and a stylus. And the stylus was fastened to a cord or a rope here with a spring down here. And then this went around another pulley. And then somewhere here it was fastened. And each one of these was driven. This was driven by a motor that had a pin. I'll draw an enlarged view of this here. Here. Each pulley had a pin in it, and it was driven by a slotted. Do I have that right? No, this rotated, and this slot was fastened to the pulley here. So this, as it rotated, it put a sinusoidal motion on this piece, and this then pulled the pulley up and down, which added length to the cord. And by having as many of these as we have terms there, they could find the resulting amplitude and record it. Well, you can imagine, these were called differential analyzers. And what's that?
It's a heck of a lot easier than doing it by hand.
Is that what the
Oh, yeah.
almanac was based on?
Well, when I started this business, that's how it was done. They produced a graph, and they got the highs and lows, and they printed them up in tables. It's a pretty slow process, but they did it, and it worked. Now that we have digital computers, it's hard to realize that we spent all that time doing these things. But the principle applies. And they're also called harmonic analyzers, the particular ones here called harmonic analyzers. Well, I mentioned that winds and low pressure affect the elevation of the tides. Before I do, I'd better describe a few terms that you'll run across in dealing with tides. There have been a number of statistics developed for tides that are useful to different people. First of all, on navigation charts, the tidal datum is mean lower low water, and that's the mean of the lowest lows. See, we have two lows. This would go like this. So the mean of the lowest lows throughout the year is called mean lower low water. That's the datum for navigation charts throughout the United States. And the reason that was selected is because of navigation. You know, you wanted to know how low the water would get, or the shallowest condition. The mean low water is the mean of all the lows. So we have mean low water, which has relevance for boundary determinations. Then we know, which is the mean of all the highs and lows. Then we have mean high water and mean higher high water. These two are used for legal terms. This one is used for modeling and for computations of the tides. It's the H0 there. And mean lower low water is used for navigation. And mean, I forgot one here. Yeah, mean tide level. I put this as mean tide level rather than mean sea level, which is probably what you've heard about, because of the confusion that arises from mean sea level. At one time it was thought that the ocean elevation was constant, so that you could use the ocean like a big level, you know, that refer to it as a elevation. But then in the late 1800s it was realized that the ocean isn't level all over, that elevation is different, and that it's changing. It's interesting to read some of the old logs of that period. San Francisco Golden Gate station, for example, at the Presidio, they installed it in 1849, and after a few years they decided that the tide gauge was sinking into the mud. So they built a huge rock crib and put the tide gauge on that. They thought this would be, on rock would be right. But the tide, it leveled out for a while, which led them to think they'd done the right thing, and then it began to rise again. And obviously sea level was rising, but they didn't understand that at the time. Then later it was realized that sea level wasn't the same around the country, and that we needed something better. So the federal government surveyed the coastline, in fact the entire country, by triangulation, and came up with what's called the National Vertical Geodetic Datum. Typically NGVD of 1929. That's when the last one was completed. They're now in the process of doing another one. In fact, it may be completed. I haven't heard lately of releveling the whole United States. But this datum is a reference for surveyors and for cities and counties and and for surveyors that is approximately mean tide level. Usually there's a few tenths of a foot difference between NGVD and mean tide level. But the mean tide level may change from place to place. So
For calculation of either the mean low water or the high water values, since you're using the extremes over what, are you counting the lowest in any month?
Oh, okay.
Year?
Yeah. There are two of those, and I should have mentioned that already. One is the annual sea level. They calculate the annual mean tide level for purposes, say, of determining sea level rise. Just a convenient period, years long. So you'll see data, mean tide level averaged over a year. Then you'll see the mean tide level averaged over 18.6 years, which is called an epoch. The actual value is 18.6 years. That's the time that the moon's precession completes the whole precession. Remember I said the moon's orbit precesses around the Earth. It takes 18.6 years for that to happen. The National Ocean Survey has adopted a 19-year epoch. The data don't warrant any finer detail than that. And they have an official epoch, which the last one is 1959, 1941 to 1959.
So I'm still confused about the low water value. Yeah, no, the top.
Mean low water?
Yeah, what?
That's the average of all the lowest lows.
Which is
Not
the
this one.
lowest?
Each day there's a lower low and a higher low,
Okay.
and a higher high and a lower high. So it's average of the mean lower is just average of the lowest ones. Then mean low water is the average of all of the low water.
When they talk about sea level, are they using this national vertical geodetic data? When they say city is certain number of feet above sea level, that's what they're doing.
When they say, this is a surveyed datum over the whole United States. So it's just a reference elevation, 0 NGVD. So when they survey here, for example, the elevations that they give you of the land, 97 feet or whatever, is relative to NGVD. It's being done. It should be done. They started about 6 years ago. It's a huge job. They have to triangulate the whole United States. So, and then once they measure it by triangulation, then they have to adjust it. They correct. Remember, did you all have surveying? Okay. Well, you know what it's like to just correct a traverse? You can imagine correcting simultaneously all these triangulation stations all over the United States.
Are they moving to geopositioning satellites for this sort of work? Or?
Not for the datum determination, but they're using satellites now, the GIS or GPS system. Is that what it's
I
called?
just heard that they think that Mount Everest is no longer the tallest mountain. They think that K2 is from satellite data.
Oh, no. No.
No, that's true.
No,
I just heard
that show. That was the first half. You were true in the second half. I just read the newspaper.
Well, the GPS system uses multiple satellites, you know, it's, I think six at present, and they plan more than that, 12. 12 was the number I think I heard. In any case, it records signals from several of them and then adjusts them to get the elevation pretty well, actually, and position pretty accurately. But the reference is still this. There's some exciting things coming, you know. Being able to measure elevations like that over large distances is something we've never been able to do. We ought to be able to measure continental drift, right? And it might be complicated. It might give us information on the surface of the Earth. Well, I've kind of gotten away from tidal hydraulics. In any case, you'll see if you're dealing with structures like wharfs or roads and the like, typically this is the datum you would use, unless it's a local city datum, which may call this 100, so that all of the sewers and so on are still positive numbers. Don't have to be negative numbers. The reason that mean high water and mean low water are used for land boundaries, that is, shore boundaries of land, is that back in Old English law, and still over most of the world, the land boundary is considered to be, upland boundary, is considered to be mean high water for navigable waters. And the reason for that is so that the riparian landowner has access to navigable waters. And in the case of the United States, where the states were given tidelands, the elevation, the land between the mean high water and the mean low water belongs to the states. And the land below mean low water belongs to the federal government in navigable streams. In streams that aren't navigable, I don't want to get into navigability, it's a legal thing, then the center of the stream is the boundary. And the boundary moves with the accretion or erosion of the shore. The mean high water boundary moves with the accretion or erosion of the shore, as long as it's a gradual process, which is a reasonable thing. And, you know, it means the landowner can continue to use his land. If it's an impulsive process, like a huge storm breaking through an oxbow of a stream or something, that doesn't count. And I don't know why that doesn't count. It seems to me it ought to, but it doesn't. So you'll find that there's huge amounts of money spent on determining the boundaries of land. And the reason is that if sediment accumulates on the boundary, the riparian landowner wants to claim it as his. And some places is complex. In one case we worked on an island developed in the stream, and once vegetation grew on the island and sediment deposited there rapidly during storms, and the island grew and it grew until it merged with the land. And the landowner claimed this 104 acres, whatever it was, the Sacramento River, as his. And the state said, no, it's ours, because the state owns the bottom of the river. You see how the controversy came about. The state won that case. I'm working on one now where there's a spit at Humboldt Bay. Somebody here from Humboldt Bay? It's a Elk River spit. It's about almost 2 miles long and about 150 yards wide, sand deposit that came from the bottom of the bay and built up there. And he's claiming it's a natural accretion, and the state's claiming that it resulted from the jetties that the Corps built. We'll see how that turns out. But in any case, the mean high water, all the marshlands around San Francisco Bay, and I'll tell you more about those, are subject to lawsuits because they're very close to mean high water. Parts of them are just a tenth of a foot or more above, and parts a tenth of a foot or so below. And the state is claiming that before they were diked off in the 1850s, they were below mean high water, so that they should be the state, belong to the state. They're obviously below mean high water now because sea level's risen and they're diked off, you know, and desiccation has made the soil shrink so that they're a couple of feet below mean high water. But that's the kind of controversy that results in uncertainties of that sort, and it's the reason that mean high water, mean low water are important. So I wanted to talk about wind setup, and I thought the easiest way to do that is to describe a simple description of wind setup that was developed long ago by I'll think of his name in a minute. But the reference is Ippen. If you want to get into this. And it's called Estuary, if I remember correctly, hydraulics. And it's 1966. And I'll draw a simplified system for purposes of illustration. Let's consider the normal water level, the still water level here, and a wind blowing in this direction, call it U, and when it blows, the shear stress on the surface pushes the surface water downwind, and what results is a setup that looks something like this. And this distance here is called the wind setup. And I'll give it this symbol S. And this we'll call H. And the wind stress on the surface we'll call tau sub S. And this distance here is X. And the total distance we'll call L. I think that's enough to describe it. What happens when the wind setup of this sort occurs is that the surface water is driven downwind, as you'd expect, so that the velocity profile, I'll draw an enlarged version of the velocity profile. This is U, positive in the X direction, let's say, and the surface of the water is here. There's a very sharp change in the water surface elevation, and it looks something like that. That is, the envelope of the velocity profile looks something like that, with water flowing downwind at the surface and upwind down below at a much lower value. And the result of that upflow is a small tau zero, I'll call it, on the bed. And the reason that you have setup is that there is some resistance to flow on the bottom. That is, the wind pushes it in this direction, but if there were no resistance to return flow, it wouldn't build up. So this turns out to be an important term. We can describe this as ds dx is equal to tau s plus tau 0 divided by rho g times h plus s. And we can describe the total from 0 to L of h plus s dx is equal to L times h. We made it a two-dimensional system, and we're just saying continuity says that the total volume here is still the same as the total volume after it's set up. That's all that says. And if you can see that if this were dry at one end, as if it actually moved it to some x0, then we'd have to integrate this from x0 to L to get the LH. It would be equal to LH. Now from limited field data, and I'll emphasize that by writing it down, shows that tau over tau s over rho g is equal to 3.0 times 10 to the minus 6 u squared, where u is the wind velocity here, divided by g. And it's usually assumed, I'll say it's assumed because it seems to, it's been assumed and it seems to fit data, that tau 0 is equal to 0.1 tau sub s. Now you can see that different bottoms would make different amounts of friction, but that's the typical value. Some authors replace this 2 with m and find some value slightly different from m in these computations. Well, this is a good point just to stop. I'll take this up next time.
What are the units on that velocity? The units on velocity?
Uh,
Are they like metric? Or
Yeah, this is in feet per second, I'm sure. You can use any set of units down to this point, but this is the one where it's. Let's see. No, that's unitless. This is dynes. Let's put it in dynes per square centimeter. Grams per centimeter cubed times centimeters. Oh, I'll work it out later. I'll keep you, or maybe you could work it out for me and tell me.
Is there much effect of salinity or constituents in the water that affects that constant?
So far, we haven't said anything about salinity. We've just said the density is constant. So this applies to a lake or an estuary. I'm going to give you more information about this.
One more question. Why is gravity on both sides of that equation?
What is?
Why is gravity on both sides?
Well, you can take it out if you want.
Right, that's what I was thinking.
Yeah, it's
Really, because you could just have
See.
tau over rho. I mean, for this particular equation, you could have tau
yeah. You can leave it. You can leave it out. Yeah, tau over rho.
equal, and then you could just have it.
Sure. Sure. This is it's typical that the shear stress is proportional to the velocity squared for turbulent flow.
And so K2 looks bigger. And then the second half of the show shows the guy who organized the original K2 with the K2 said, well, I can't live with that. You can measure them both on the set of the same work. So he organized.
Oh yeah.
And what was this one?
That's U over U star.
What was the configuration that we were dealing with there? We've got a pipe.
Oh, that's see. This is just this is for broad no